That's defined as moles per liter, and it's capital M, right? That's what we call that. And what are the other concentrations that are important for other fields but not as important for chemistry? Does anyone remember? There are percent concentrations. What were the 3 different percent concentrations we could have? Mass to volume, right? That was one that's relatively important, right? That's grams per 100 milliliters. What about, did anyone have any other ones? So mass to volume, and then 2 variations of each of those fundamental units there. Right, we have percent mass to volume. What was another one that we had? There was volume to volume percent, right? And that was milliliter per 100 milliliters. And what was the last one? Mass to mass, right? Mass to mass percent. That was grams per 100 grams. Those are the 4 different units of concentration that we talked about. Just be comfortable with, if you're given a percent mass to volume solution, what is the amount of solute within a given volume, and then what is the concentration in mass to volume percent if you have this many grams dissolved in 250 milliliters, for example, right? Those are the types of questions we could answer using those concentrations. And we found that using these concentrations, if we wanted to find the amount of solute, how did we use the volume of solution and the concentration value? Right, if we want to find the amount of solute, whether it's grams or moles, right, we could use the volume of solution and the amount of, sorry, not the amount, sorry, the volume of solution and the concentration value for that solution. Yeah, it'd be the concentration, right, times the volume is how we get, right? Because if we look at any of these units, all of these have some sort of amount of solute per unit volume of solution. So if we multiply any of these, for example, molarity times a liter, liters cancel out, and we're just left with moles, right? So that will always give us the amount of solute. C being our concentration value, and V being the volume of the solution, right? So that's how we define these. This is the concentration, and this is the volume of solution. All right, so that was one way we could use our concentration values. Another way we could use our concentration values was we could find the volume of solution needed for a specific concentration given a certain amount of solute, right? So how would we find the volume of solution using the concentration and the amount of solute? Right, so the way that we did this with the molarity, where we multiplied this by a liter, those cancel out, leaves us with units of moles. What if we wanted to find units of liters, right? How could we combine these values, right? This is like dimensional analysis, right? We're looking at the units to seeing how the units work out. How could we use concentration and the amount of solute, either moles or grams? Yeah, if we take the amount of solute and divide that by the concentration, that should always give us units of the amount of solute, or the units of the volume of the solution. So if we take the amount of solute and divide it by the concentration value, that'll give us the volume of the solution. All right, so let's look at molarity, for example. If we take the moles of solute and divide it by molarity, what are the units of molarity? Moles per liter. What happens to the units of moles? These cancel out. And what about 1 over liters? How does that simplify? Right, if you have a fraction of fractions, yeah, it simplifies because that goes to basically 1 over 1 times liters over 1, which is just liters, right? This is whenever we have a fraction of fractions. So just to review, if you have 1/2 over 1/4, that's like the same thing as 1/2 times 4 over 1. You just invert what's in the denominator. Right, you can always do that with fractions. So if you have moles over moles per liter, moles cancels out, and the liter goes in the numerator. So that just goes to liters. Right, and if you look at that, this doesn't matter which type of concentration we're using, because they always are going to give you the amount, or the volume of the solution, or the amount of solution if it's grams to mass percent, by just taking the amount of solute and dividing it by the concentration value. Right, so that was a couple different calculations that we looked at. And then we also looked at, how can you complicate these problems? And one of them was, well, if you want to find molarity, right, can you measure moles in the lab? No, you can't measure moles in the lab. What do you measure in the lab? The grams, right? So if you want to calculate molarity, you have to get from grams. You have to use what to go from grams to moles? The molar mass, right? You use the molar mass to get to moles, and then you divide it by the volume of the solution you need for your desired concentration. Right, so those were where we ended off last time. Right, so if we have, for example, a question that says how many grams of sodium carbonate or sodium bicarbonate are in 325 milliliters of 4.5 molar solution of sodium carbonate. Right, so the first thing you do here is you identify what's given to you and what you're trying to solve for, right? So what are you trying to solve for here? We want to find the grams, right? This is the amount of solute, right? We want the grams of our solute, and we're given what? What two values are we given?
325.
We're given, the volume, and what's this? Yep, the concentration of the solution. Right, so given a volume and the concentration, what are the grams of sodium bicarbonate in solution? So why don't you guys take a second and see if you can figure this one out. We get the amount of solute from a concentration and a given volume. What's the general formula for that? What is this? Yeah, we use the molarity, we use the concentration and the volume, right? And the amount of solute is equal to what in terms of any concentration value and the volume of solution? What did it just say? On the last time slide. C, which is our concentration, times the volume of the solution, right? So what's our concentration value here? 4.5 molarity, right? And what's our volume? 325 milliliters. So let's plug that in, right? And we're gonna get amount of solute, and we'll see, we're just gonna start from here, and then we can change things as we go to see if we need, how we're gonna get to grams, right? So we'll start from our concentration, which is 4.50 molarity times 325 milliliters, right? This doesn't really tell us anything or help us anything yet, because leaving terms in molarity and milliliters here, if we multiply those two units together, nothing happens, right? We just get molarity times milliliters. So how can we rewrite molarity so that it can be useful to us? Moles over liter, right? So this is the same thing as 4.50 moles per 1 liter, right? That's how molarity is defined. And we have that times 325 milliliter. Moles is a unit of amount of solute, right? So that's okay to go to, and we know we can go from moles to grams afterwards. So we were like, okay, well, this is good, because then if we can cancel out the units of volume, then we will end up with the amount of solute. But what's the issue here? Yeah, we're in milliliters, right? Milliliters don't cancel out with liters. So how do we fix that?
We just convert the.
We convert milliliters to liters, right? So we have to make sure our units are working out. And how many milliliters are in a liter? 1,000, right? Milliliters per 1 liter, right? So all I did is I included my unit conversion in this step. Milliliters cancels out, and now liters will also cancel out here. All right, liters and milliliters both cancel out. I'm left with just units of moles. And so when I plug that all in, it'll be like 0.325 times 4.5. And what do you guys get when you plug that in? Divided by 1,000, right? Yeah, so it should be 1,400, so it'll be like 1.4 or something, is around there? Right, because you have to remember to make sure you divide by that 1,000 because that's the conversion from milliliters to liters. We have to include that 1,000 in there. So it should be 1.4 what? 1.46 moles of what? What are these moles of? Yeah, sodium bicarbonate, right? So NaHCO3. All right, so now we have moles of NaOHCO3 in our solution. This is how many moles are there. The problem asks for how many grams, though. So how are we going to get to grams? The molar mass, right? We can go from moles to grams, mass to moles, using the molar mass, right? So we go from moles to grams, moles, using the molar mass of what? NaHCO, sodium bicarbonate, right? So we start from moles, and how many moles do we have? 1.46, right? That's what we just solved for. We just solved for the amount of moles in solution, right? So we just solved for it. So we're continuing the question, we're continuing the problem, and we're using the value that we just calculated, right? So we have 1.46 moles NaHCO3. And we use the molar mass, and how are we going to use the molar mass? We're going to divide or multiply by it. What are the units of molar mass? So before we even plug in the number, what are the units of molar mass? Grams per mole, right? And we want to end with units of what? Grams. So where should the units of grams be? In the numerator, right? So it'd be grams, NaHCO3, per 1 mole NaHCO3, right? That's how the units are going to work out. And what is the molar mass of sodium bicarbonate? 84.01, 16 times 3 is like 48 plus, yeah, that sounds about right. Sodium is what, 22? That sounds right. 83 point what? 01 grams per 1 mole. Did everyone get that? 83.97? Those are close enough, right? They're probably depending on what periodic table you use, they could be, but you got 83.97. Anyone else get, which one, someone break the tie?
Well, hers might be, because I said 84.01, not 83.
Oh, 84.01. Yeah, so that depends on which periodic table you use. Right, because if the periodic table has more or less decimal places, that'll affect what answer you get. But that's roughly about the right answer. And how did you get the molar mass?
Adding each.
Right, you add up all the molar masses of every atom that's in the molecule, right? So you need to keep track of the formula subscript and which atoms that you're looking at, right? So you have to be able to identify that. And again, that's what you want to be very, very comfortable with. So moles of sodium bicarbonate cancel out, and we plug this in, we get 1.46, so I'm guessing we get something like 120 something? What do you guys get for? 122. 122.7?
Yeah.
122. We have 3 sig figs though, so we'll keep it at 3 sig figs. So we'll do 123 grams of sodium bicarbonate. Right, so that's how many grams of our solute is in a 325 milliliter solution of 4.5 molarity. Right, another way that you could phrase this question is if I have a 325 milliliter flask and it's only calibrated for that volume, how many grams do I need to dissolve in water to get a 4.5 molar concentration solution? Right, that's a practical application of the same question that we're answering here. This is explicitly asking how many grams are there in this volume. But I could say how many grams do you need to dissolve in 325 milliliters of water to get a 4.5 molar solution? All right. Any questions on this? How do you guys feel about that? Thumbs up, thumbs to the side, thumbs down? Thumbs down. Thumbs to the side, thumbs to the side. I see mostly thumbs to up and thumbs to the side. All right, so then let's try a challenge problem that combines both chemical quantities and our now understanding of concentrations. All right, so say you mix 320 milliliters of 0.5 molar silver nitrate with 450 milliliters of 0.85 molar sodium bicarbonate. I think it's a question. Sodium carbonate. How much silver carbonate will precipitate in grams? And our chemical equation for this is AgNO3 aqueous plus Na2 CO3 aqueous goes to, let me move this over, Ag2 CO3 solid plus NaNO3. All right, so here we're going to have a double replacement reaction. And you're given a chemical reaction. You're mixing two different solutions of different concentrations of different volumes together and asking how many grams will you precipitate, right? So yeah, if you can't read anything, let me know. What is it? What was it? And oh, the G got deleted. Or did it get moved? Oh, it got moved here, huh? I accidentally clicked it. Precipitate, which one? Oh, it's all the way over here. AgCO3, and this is grams. All right, we're just gonna assume this reaction goes in one direction. So you ask how many grams are gonna precipitate. And this is something you guys have actually done, right? You guys have done precipitation reactions where you just mix two solutions together and all of a sudden a solid starts forming, right? And now you have the tools to be able to predict, well, how much product am I actually gonna make? Or what's the theoretical maximum that I'm gonna make here? All right, so this is a very layered problem, right? Involves almost everything that we've talked about from chemical quantities up to this point. It includes solutions in this problem as well, right? So what's the first thing you need to do whenever you're given a chemical equation? You need to balance it, right? You need to make sure it's balanced, right? So the first thing you're gonna start off doing is check to see if the equation is balanced, and if it's not, then you balance it. Then what are you gonna do for a problem like this? Right, what type of, I guess, how would you approach this problem, right, if you saw this? What do you think how would you approach this? Or what do you think? Yeah, you're gonna use the volume of each solution, right? And you're given a concentration. Yep, and if you use the concentration of the volume, what can that tell you? The moles, right? That tells you the amount of solute if you're given the volume of that solution and the concentration. So why would you want the moles of each reactant here?
Then I'll be able to go to grams.
You can go to grams of the reactant, or what else could you do from moles of the reactant? Not quite the molar mass, it is the molar something, but
The mole-to-mole ratio.
you can use that to find the moles of the product, right? Once you find the moles of the product for each reactant, then you know which one of them is gonna be what? One of them is gonna limit the reaction, right? So one of them is gonna determine how many moles of product you actually make. Then once you have the moles of the product from the limiting reactant, what do you have to do? All right, what's the question asking for?
Have to, get the grams.
Yeah, you have the moles of the product, and now you need to go to the grams of the product. Right, so that's the general skeleton for how you're gonna approach this problem, right? The solutions are now gonna be used to find the moles of our reactants. Previously, we'd only been given the grams and used the grams of the reactants to find the moles before you could convert it to the products, right? Now you're using the solution concentrations to find the moles of each reactant. Okay, so see if you guys can spend 5 or so minutes to figure that out, at least start getting that going, right? So that means you're probably gonna involve some sort of flow chart. You can treat this as a unit conversion problem and a limiting reactant problem. Second step was convert each reactant concentration to moles. Okay, so what's the balanced chemical equation? What are the coefficients? What's the coefficient that goes in front of silver nitrate? All right, what coefficient goes in front of this compound, silver nitrate here? 2, right? We get a 2 in front of silver nitrate. We balance heteroatoms first, right? There's 2 on this side and there was only 1 on the other side. So we balance the silver first and we get 2 silver nitrates. What goes in front of the second compound, sodium carbonate? It should be a 1, right? So we're not gonna put anything in front of there, right? We don't change that 1 at all. And then what about for silver carbonate on the right-hand side, the product side? Right, silver's already balanced. Carbonate we didn't change at all, so that one's okay right now. And what about for sodium nitrate? 2, right? Because the first thing we notice is sodium, which is only in the sodium carbonate on the left-hand side, has 2, and there's no 2 on the right-hand side. So we put a 2 in front of the sodium nitrate, right? So now we have our balanced chemical equation, right? We have 2 nitrates on the left side, 2 nitrates on the right side, 2 silvers and 2 sodiums on each side. Carbonate, we have 1 of each on both sides. All right, so that gives us our balanced chemical equation, which we're going to need in a little bit. The first step, though, is to find the moles of each reactant using the concentrations and the volumes, right? The relationship that we use for this is that the amount of solute in moles, grams, whatever our value of concentration is equal to, is the concentration times the volume, right? Our concentration of silver nitrate is 0.5 molar silver nitrate for that reactant, right? The volume was what? (320 milliliters), which is 0.320 liters, right? Why do we need it in liters? So they can cancel out, right? So the liters can cancel out, and we're just left with units of moles, right? We want units of moles because we're ultimately looking for the moles of our product, right? So units of liters cancels out, and we get, in that solution, we added 0.16 moles of silver nitrate. All right, all we used is the solution concentration and the volume of that solution. For sodium carbonate, we have an 0.85 molar solution, which is the same thing as 0.85 moles per 1 liter, the amount of solute for a given volume of solution in liters, times the volume, which is 0.45 liters. We need it in liters, so units of liters cancel out, and we end up with 0.383 moles of sodium carbonate. All right, how many people got this far, at least? Okay. A lot of, that's how people raise their hands. I guess no one wants to see anyone else, anyone behind you that you're raising your hand. Right, so what do we do once we have our moles of reactants now? If we use the molar mass here, what would we convert these into? Grams, right? Grams of what? Of the solute, right? We would get grams of solute. And what are we trying to find grams of? Of the product side of the reaction, the precipitation, right? So we're trying to find the grams of the precipitate. So if we convert it into grams right now, it would give you the grams, which you would then have to convert back to what? Moles, to then get moles of reactant, because then you can convert moles of reactant to what? Moles of product, right? You can go from moles of reactant to moles of product. Remember, we always have to go to moles to be able to go from reactants to products when we're talking about chemical quantities of one compound to chemical quantities of another compound. You always have to go to moles first, right? So here we already are at moles, right? We use the solution concentrations to get to moles. All right, so how are we going to go from moles of our reactants to moles of our product? Use the molar ratio. And where do you get the molar ratio from? The balanced chemical equation, right? So we're going to go from moles reactant to moles product for each of our reactants. Why do we have to test each of our reactants? Because we don't know which one's going to limit the reaction yet, right? We have to say, okay, we're mixing non-stoichiometric amounts. All right, we're not mixing exactly 2 moles of silver nitrate and 1 mole of sodium carbonate, right? This isn't 1 mole, or this isn't 2 moles, and this isn't 1 mole. We're doing non-stoichiometric amounts, which means that one of these is going to limit the reaction, how much product we can actually make. So we're going to use the molar ratio to convert between the two. And is it going to be the same molar ratio or different molar ratios for each reactant? All right, let's do this. For each reactant, we want to go from moles of sodium nitrate, 2 moles of, or sorry, not sodium nitrate, silver nitrate, 2 moles of silver carbonate. And we also want to go from moles sodium carbonate to moles of silver nitrate. Right, we want to do that for both of them. How many moles of silver nitrate are there per mole of, per how many moles of sodium carbonate? Where do we get the values that we're going to plug in here? The balanced chemical equation, right? That's what gives us the molar ratio. So how many moles of silver nitrate are there per reaction?
2.
2, right? Because we get that from our balanced chemical equation. 2, 2, 1, and then 1, right? That's where we're getting these values from. So we have 2, and then how many moles of product does that create that we're looking at? The product of interest. 1, right? Because our silver carbonate only has a 1 in front of it, right? It doesn't actually show the 1, but that's what we assume, per 1 mole. And what about for sodium carbonate? It's a 1-to-1 ratio, right? So is it the same molar ratio for both of our reactants? No, it's not. And that means that it takes a different number of molecules or moles of molecules to have one reaction or a mole of reactions happen, right? So this is what's going to affect how much product we make now. Or we're mixing things in non-stoichiometric amounts, meaning different moles than what their stoichiometric coefficients are in the balanced chemical equation. So we have to determine which one limits the reactants. And so what's the molar ratio that you're going to use for your first reactant? All right, what's the conversion factor? What's going to go in the numerator and what's going to go in the denominator? Right. Silver nitrate in the denominator because we want the product in the numerator. We want the moles of our product in this case, right? So that's going to be 1 mole AgCO3 per 2 moles AgNO3. And it's the same thing for our other reactant, right? We're still going to have the same product in the numerator, CO3, sorry, this should be Ag2, per 1 mole Na2CO3. That's a conversion factor that we're going to use. All right, so now that we've gotten to this step, see if you can find the grams, right? Using all the information, determine the grams of product that are going to be made. All right? Just because, so if you're done, you can work on a question part 2. What is the concentration of NaNO3 in the resulting solution? Right, so if you are done with the first part of the question, ask, what is the concentration of the other product in the solution, right? That's still in the aqueous phase. What is the concentration? So think about how you would then solve for that. Or the second part together, or the first part together then. All right, so you convert it to each moles of each reactant into moles of product, right? Which means that we start from, let's look at silver nitrate first, 0.16 moles of silver nitrate, AgNO3. And we use the molar ratio to convert that to moles of product, right? And then we have 2 moles AgNO3 per 1 mole silver carbonate, Ag2CO3. Right, what happens to the moles of our reactant? They cancel out. And we're left with moles of our product, which is what we want to determine the limiting reactant. And so when you do this, you should get 0.08 mole Ag2CO3. We'll do the same thing for our other reactant. 0.383 mole Ag or Na2CO3. And I can tell you, because I know it's a 1-to-1 mole ratio, we're gonna have the exact same amount of product. So it'll be 1 mole Ag or Na2CO3. Make that look a little neater. That didn't look neater. Per 1 mole Ag2CO3, right? Because we're only analyzing the amount of precipitate that was made, right? Which is our silver carbonate molecule. That's what's going to be precipitating here. So we're only analyzing that product. We're only focusing on that product for right now. That's going to give me 0.383 moles of silver carbonate. Right, so which one of these is our limiting reactant then? Top or the bottom? Vanessa? We will convert to grams, right? But how do we know how many grams are going to be made? How do we know we don't convert this to grams or this to grams?
Does it accidentally convert both of them to grams?
It'll give you the same answer if you do that. So if you convert both of them all the way to grams, it'll give you the same answer in the end. It's just at this step you don't have to do that twice. You only convert it to grams once. But yeah, because you can identify the grams, and that'll tell you what's the limiting reactant too. It's just an extra step you don't have to do, but you can do that if you want. So which one of these is the limiting reactant? Top or bottom? Top, right? Why is the top the limiting reactant? Because it's less, right? It makes less moles of the product, which means that that's the maximum amount we can make is whatever makes less, right? We don't have enough silver nitrate to make more of our product in this solution. So this is our limiting reactant. So now if we want to calculate the grams of product that we make, what do we need to do? Convert to grams, and what are we going to convert to grams? The limiting reactant moles, right? We're going to convert this to grams because this is actually the real amount of grams that we're going to make. If we convert this to grams, that's not possible because we don't have enough silver nitrate to make that many grams, right? So we're going to convert the limiting reactant to the grams of product. So we have 0.08 moles of Ag. You mind closing the door, Sam? Thank you. Yeah, Ag2CO3. And how do we convert this to grams? What do we use? Right, whenever we're going, what are we converting this to? We're converting moles to what? Grams, right? And how do we go from moles to mass? Molar mass, right? So we're going to use the molar mass, and the molar mass value is 275. And what's going to be in the numerator? What units are going to be in the numerator, and what's going to be in the denominator? Grams in the numerator of AgCO3, and then what's in the denominator? Moles of AgCO3, right? Because we want moles to cancel out, we want to end with units of grams, and it should be 275.75, I believe. Units of moles cancel out, and that gives us the moles of product that we create. And when you guys finish that, what did you guys get for your amount of grams? It should be pretty, huh? 22 grams. We got 22. Let's see, how many sig figs did I give you? 2. That's fine. 22 grams. 22 grams of silver carbonate. So this is the amount of precipitate that you should expect in solution if things are 100% efficient, right? In reality, you know, maybe you heated it too much, your solution boiled, exploded all over the fume hood, so you lost a lot. But this is theoretically the maximum that you should make. It deleted for some reason. 22 grams of your silver carbonate. So this means for this process, our flow charts can be, expanded, right? We don't just have to start from mass of reactant. We can start from concentration and volume of reactants to then get our mass or concentrations of our solutions, right? So if we had a flow chart, we still know we want to go from moles of A to moles of B, and we know that we can go from mass of A, grams of A, to moles of A using the molar mass of A, and we can use the molar ratio to go between them, and we can use the moles of B then to go to grams of B using the molar mass of whatever compound B is, right? But now we have something else that we can add, right? We can start from the concentration of the solution, use the volume of that solution to also go to the moles, right? So we can go from the concentration of A, using the volume of solution to get the moles of A, right? That was all we did is we just changed the first step. We didn't use the molar mass to convert, we used the solution concentration to get to moles of A. Once we do that, then it's the same idea. We use the balanced chemical equation to then get to moles of B. And then we went up to grams of B from there. But the next part of the problem says, well, what if you want to know the concentration of the other reactant or the other product, right? Because the other product, if we look at it, is an aqueous, meaning it's dissolved in solution. It's still floating around in the water. So you could ask the question, well, what's the concentration of the other product here? Right? And so if you started from where we did, which was the concentration of A, we already converted that into moles of A of each reactant. We found the limiting reactant. We use the molar ratio to get the moles of a product, right? We have to redo that for the other product in this case. How are we going to get to the concentration of whatever B is? What are we going to use, right? We would now want to find the concentration of B. What would we need to know if we have the moles? Yeah, you need the volume of the solution, right? So the same thing that you did before, you do for this path getting to the concentration of B. All right, so we're expanding what this flow chart can look like, right? Because we don't just get to moles from the mass, we can get to the moles from the concentration, and if we start dealing with gases, we can get to moles from the ideal gas law eventually too, right? So we're just going to keep expanding this flow chart, but the same thing, the same important realization here is that you're always going to have to go to moles of whatever it is you're converting between, because that allows you to go from moles of one thing to moles of another thing, right? That's the common factor in all of these types of conversions. How you get to the moles will change, but you're always going to moles, right? And that's pretty much I'd say the main takeaway from this course is you need to go to moles to get to something else, to moles of something else. Okay, so for the last part of this question, what is the concentration of the other product in solution, right? So you don't have to go through and do everything from the beginning again. You already have the moles of each reactant. So using the moles, right? So start from moles of each reactant and use that flow chart to then get to the concentration of that reactant. And how do you know which reactant is going to give you the moles of your new product or the other product that you're looking at? All right, you had, in the first step, you identified the limiting reactant. For your other product, is that still going to be the limiting reactant? What do you guys think? it should still be the limiting reactant, right? Because this is the limiting reactant for how many times this reaction can happen, right? The amount of times this reaction can happen is still determined by the limiting reactant. It doesn't matter which product we're looking at. All that we're doing when we do this is we're just changing this ratio, right? Because now we're not looking at silver carbonate, you're looking at sodium nitrate. But that just means that both of these are gonna have this number change on both sides, right? So both of them are gonna end up just being multiplied by 2, a smaller number multiplied by 2, and a bigger number multiplied by 2. The smaller number is still gonna be smaller even if you multiply it by 2, right? But that tells you the thing that does change is the moles of product that you will get, right? The moles of product that you'll get is what actually changes because you're talking about a different product. All right, so see if you can determine the concentration of this solution. It's taking like 3 minutes or so to determine the concentration of your other product in solution. All right, who's still working? So I have the solution up here, but if you're still working, don't look. We'll talk about it together. Okay, so what was the breakdown of what I did? I took the moles of my limiting reactant and converted that to moles of my other product, right? So I know my limiting reactant is still my limiting reactant. It was 0.16 moles. So, and that was the silver nitrate, right? That was the moles I already calculated. That's how many moles I mixed into the solution. I then used the molar ratio, which I get from the balanced chemical equation. For every 2 moles of silver nitrate, 2 moles of sodium nitrate are made, right? That's where you get that ratio from, or balanced chemical equation. That allows me to go from moles of sodium or silver nitrate to moles of sodium nitrate. And I get 0.16 moles, right? It's a 1-to-1 ratio or 2-to-2 ratio. So I end up with the same moles of that product. I need to calculate the concentration of this solution, right? So I don't have to use mass at all anymore. I'm already in units of moles. And so I just use my definition of what molarity is the moles of sodium nitrate divided by the volume in liters of the solution. My moles of sodium nitrate is exactly what I calculated, right? That's where I get that from. And then the liters is the sum of the 2 solutions that I mixed together, right? The volume of my new solution is the final volume of mixing them together, right? So that's the total concentration in the of sodium nitrate there. It's because this is only created after the solutions are mixed together. So the amount, the moles of that solute, sodium nitrate, is in a total volume of the sum of the 2 volumes. Right, so that was 0.32 liters plus 0.45 liters. You plug that in and you get a concentration of 0.21 molar sodium nitrate. Okay. Are there any questions on that, or where I got these values from, or why I put certain things in certain places? The key concept, again, is when we get everything in units of moles, that's what allows us to go to other things like mass, molarity, even energy, if we were talking about energy. All right, so this is a challenging problem. This would be too hard for an exam, so I won't give you a question like this on an exam, at least not something this long in detail, but this encompasses almost everything we've talked at this point, right? We had to use concentrations to get the moles, balance a chemical equation, determine the limiting reactant, then use that to determine the grams of a product using the molar mass conversion, and also the concentration of a product using our new total volume of the solution. All right, so this is a lot, but it encompasses everything that we've talked about to this point. So if the whole thing on its own is intimidating, that's normal, but each individual step should start to make sense, right? Why we do each individual step, right? If I just gave you the moles of a reactant and said this makes this many moles of product, or how many moles of product does it make, assuming you have excess of everything else, what's the concentration? This last step should be doable for you guys. All right, if there's no questions, then we'll end that here and we'll start